This is IAT 355, Lecture 10, where we're talking about graphs. We're going to build on the previous suite of lectures, Lecture 9, parts 1 through 5, where we're now explicitly going to be talking about graphs. So I'm going to revisit the node link diagram piece as it applies to graphs, and then we'll talk about interaction with graphs of various kinds and force-directed layout. So that's going to be our topic for today. We're going to be talking about, first, node link revisited, or Redux. So the definition of graphs, once again, it's a mathematical structure used to model pairwise relationships between objects. And what that means is that you have a number of objects that are boiled down to each individual object is represented by a point or a vertex or a node. And the relationship between those two nodes is indicated by the presence of an edge or an arc or a line segment, if you draw it, between those two nodes. And you can have graphs that are very, very complex. So example relationships are each of the nodes represents a city, and the edge represents an airline flight between two cities, or the presence of airline flights. Another node and link relationship in transportation is you have stops along a train line. Every single stop is a node, and the train line between those two stops is represented by the link between them. And another example of that, we'll talk about these later on, is representations among friends in your favorite social networking site. So what is a graph? So once again, we have something very similar to the matrix layout up here. Up at the top, you see a layout which in each of these three things is about a 3-node graph. So there's node 1, node 2, and node 3. Okay, and those are the nodes in the graph. And so those nodes can be represented visually in this node link diagram here. They can also be represented by this adjacency matrix, and we talked about the matrix representation in lecture 9.5, right? And so across the top are is the list of vertices or nodes, and down the side is the same list of vertices or nodes. And 0 is on the diagonal, indicating there's no connection from a node to itself. 1 indicates that there's a connection between node 2 and node 1. Similarly, there's a connection between 2 and 1 here. So this matrix is symmetric and redundant. So the upper diagonal, the upper triangle or the lower triangle contains all the information you would need just for regular graphs. And there's a connection between node 3 and node 2, and that's indicated by column 3, row 2 has a 1 in it. Same with column 2, row 3. And so anyway, this third thing is an adjacency list. This is the kind of thing you might have as a more compact representation in a data structure. You have a array or a list of something of nodes, and then off of each node hangs a linked list or something of edges. It's more compact when the number of links is significantly less than the number of nodes you might have, about the same number, or maybe a factor of 1, 2, or 3 the size of the number of nodes. This thing tends to consume a lot of space because there's a representation for every possible connection, and a full matrix like this is probably more useful if you have very dense connectivity. Okay, so let's talk about some more graph terminology. I'd said for trees, acyclic, or you can't make a cycle, here's a graph that actually has a cycle in it. So we have 7 nodes, node 1, 2, 3, 4, 5, 6, 7. And what a cycle is, now that we actually have an example we can look at and trace it easily, we can trace a path from a node, say from node 1 here, from node 1 to node 2, 5, 7, 6, back to 1. We don't repeat nodes and we don't repeat edges in that cycle. There could be more than one cycle in a graph, could be dozens, hundreds, who knows how big, depending on the size of the graph. In this instance, there's just a single cycle. So this thing is not a tree because it has a cycle in it. So that's the first point. Graphs can have cycles. I showed you the example of that. Graph edges can be directed or undirected. This is an undirected graph, meaning each edge indicates a connection between the two with no implied directionality. The degree of a vertex is the number of edges connected to it. So the degree of node 2 here is 3. The degree of node 3 here is 1. The degree of node 1 here is 2. Node 6 is 2. Node 7 is 2. Node 4 is 1. And node 5 is 3. Graph edges can have values or weights on them. This is shown here as unweighted, but an example of a weighted graph could be, if this is a transportation network, the number of people traveling along from this station to this one, and from this station to this one. The weights would be the number of people per day or per week or whatever is appropriate for the application. This thing shown here doesn't have weights shown explicitly, and the thicknesses are all the same, which also implies a lack of information about weight. So a directed graph is a graph in which each of the edges are, the terminology is arcs actually, and each arc has a starting and an ending node. So this arc here, that curved thing, that has, that's an arc going in one direction, and there's an arc going from node 1 back to node 2. Similarly, node 4 points at node 5, 6 points at 7, 6 also points at 1. And you could imagine that, for example, there is some information about information or traffic or something flowing from, say, node 6 to node 7 and node 1, flowing from 4 to 5, and flowing from 7 to 5 to 2. So essentially, all of the information kind of flows to 2 here. This thing also has a directional cycle in it. You can go from 2 to 1 back to 2. You don't repeat edges or arcs, and you don't repeat nodes, and that's possible because there's 2 edges here. The thickness is also meant to indicate the visualization of the weight of each of those arcs or the weight of those edges. Thicker means more, typically. You would also imagine that you don't have negative weights in this depiction, although it could be the case that there is such a thing as a negative weight. Somehow or other, it depends entirely on what the application is. So the concept of a graph is very flexible, and so it could be perfectly sensible for there to be negative valued weights on an edge. Okay, so as we've said, in all of Lecture 9, trees are a subcase of graph that don't have cycles. They typically have directed edges, although we didn't really emphasize that in the Lecture 9 series. And there's a specially designated root node almost always, and that's there for convenience because, generally speaking, the directions all flow in one direction from the root down to the trees or the leaves and so on and so forth. And that's typically the way you do trees in a data structure that uses pointers and so on. So we've spoken at trees at length, so I don't want to go further into that. So the stuff we're going to be talking about in terms of visualization, once again, comes from Munzner's chapter about arranging networks in trees. Really, for graphs, we're only concerned with the matrix representation, which we've sufficiently covered, and node link diagrams. Those work for networks or graphs in general. The enclosure things, such as tree maps, doesn't really work well for networks because you would have to add some visual representation in order to represent visual links. And, given that containment is the thing that indicates the parent-child relationship, adding links, just would be troublesome. So we're not going to do that. So for this lecture, we're just going to really focus on using visual representations that are really especially built for graphs. The way that graphs are used is that any number of data sets can be modeled as graphs. Some can be really surprising that the representation is transformed into a graph in order to make it computable in a different way. But we're going to focus on straightforward representations of graphs. things that are kind of naturally networky and have a natural visual representation. So things like the telephone system, the interconnections among the internet, major hubs, and the distribution network for an online retailer. The retailer is sending stuff out. They're sending stuff to the warehouse and sub warehouses, and then they are connecting, via delivery companies to the recipient, to the customer. That's a network, and if you're interested in managing logistics, you do want to know how the connections are working. The call graph of a large software system is an example of a network. It's not necessarily tree-shaped. You might have large numbers of objects in the software architecture, accessing and building instances of a few kind of basic fundamental objects, and they are calling methods in those objects over and over in order to do certain things. So it's typically, it might end up being a directed graph. It's acyclic, but there's reuse of things that are might be used as trees. And so that would be interesting. For example, you might not think that a lot of your resources are taken up by making calls to some particular part of your software system, but in drawing that call graph, you might find, oh my God, something's really, really heavily using this particular class, and I better make sure that that class is as efficient computationally as possible so that the program doesn't run slowly. And so there's some other examples there: semantic map in an AI algorithm, or sets of connected friends, things like that. So one of the things that can also be used for, and we'll talk about these examples in a little bit more detail right now, is understanding relationships among entities like countries or localities. So there's some examples of that, and one example I'm going to show you right now is Krempel and Plumper's study of world trade between countries around the world at 2 times, one in 1991 and one in 1992. So let's show what that looks like. You can get access to these graphs at this website, although it gives you a little warning about, being unsafe. It's not doing anything exotic, but, you don't have to go there. But anyway, I just wanted to give a reference where it comes from. So here's world trade in 1981. China isn't present in this. I think probably they started with China kind of not really participating in the world trade system at the time, and they used the same suite of countries for 1992 as 1981. So China really just started opening itself up in the very early 80s, and so world trade with China was very, very small at that time. So they're not present in this graph as far as I can tell. However, in 1981, you can see in yellow is European countries. It's kind of the big player in European trade is Germany, trading with the Netherlands, the UK, Belgium, Italy, France. Spain isn't strongly represented in here. Spain's there, I think, in this, but Spain was not so economically active, and they joined the European Union, I can't remember exactly when, sometime in the mid-1970s, and started to gear up their trade at that point. In 1992, the picture has changed a bit. The trade has grown bigger between Germany and the countries I just mentioned, but also Spain is now much more involved in world trade. And the trade amongst all these countries has grown significantly. Another trade relationship that is of long standing is between Canada and the USA. Very large trade flows between those two countries, significant trade. It didn't really change all that much, even though the Free Trade Act came into effect in 1987. Not a gigantic enough change, but trade with Mexico improved. The NAFTA version of free trade didn't start happening until the mid-1990s. So that's why the trade between USA and Mexico is not so salient in this thing. Trade between Japan and the USA was very significant in this era, but one of the things that you can see in this graph is that trade between Japan and other Southeast Asian countries grew significantly between 1981 and 1992, and among other reasons, that was because Japan had created a manufacturing economy for itself, and then started to offshore its manufacturing to cheaper labored countries in Southeast Asia, such as Thailand, Taiwan, and Indonesia, Singapore, and countries like that. So that gives you an example of what's going on, but of course you can see that this looks like the proverbial hairball. It's not quite so hairy as a hairball, and if it were interactive, you could sort of pick off examples and focus, but still, this is pretty much a complete graph. Every node is connected to every other node, and really the only question is, what is flow? And I kind of got right into interpreting what this graph is about, but clearly the primary two depictions is first off connections, color to indicate region. East Asia is in red, Europe's in yellow, North America is this blue color. Green is European countries outside of the European Union, so there's Switzerland, for example. And the size of the node and the thickness of the line indicate trade volume in some currency or other. Here's another world trade map. This is a little bit more recent. This is 2007. It's another node link diagram. And unlike the previous one, this one shows locality more or less directly. So this is kind of a world map. Here's Canada and USA on the left. Mexico is here, kind of at that location, partially for convenience. And here's the various Caribbean countries. There's Venezuela, Panama, Ecuador, Peru, South America now. Okay, so these countries are all participating in the world trade system, although to a modest degree. Here's African countries here. There's that's Nigeria, South Africa, Mozambique, Zimbabwe. Here's India, the Gulf states, Yemen, etc. And here's Europe, and again Germany, France, Britain, Netherlands, Italy, etc. And over here is East Asia, China, Japan, and I think that's Myanmar, and here's India. And so what this is not indicating the size of the countries, this is indicating major two export partners. So an arrow goes out from each of these nodes to the other to two other nodes, and the reason for that is to limit the intensity of the overdraw, because presumably every country trades with every other country, even if it's only $10,000 or something like that. But they have a cutoff in this graph so that it can be comprehensible. And you could sort of stare at this thing and gain an understanding of how world trade is. And clearly, world trade in the European domain is very, very intense. So what the purpose of these graphs is doing for us is to understand network flows and network relations. And even information with a geographic content can best appear as a network. The previous one showing world trade is kind of doing a geographic embedding, relying on your knowledge of world geography to understand where the countries are and to guess or infer properly the country abbreviations. Another variant of graph drawing that you do see is in transportation networks. The various rail maps of subway systems around the world are examples of graphs that have been distorted and refined so that you can find your way inside the subway system without having to worry. And your primary focus is, I need to get to locate some station. I start at station A, I'm getting to station B, and I have to change trains somewhere. And so where are the interchange spots? How should I travel to get there? So finally, for lecture segment 10.1, what I'm going to do is talk about a case study. So this case study is a case study of AT&T long-distance telephone network. This is big switching offices that are wired up to other big switching offices around the USA. And that network has 110 nodes or 110 switches. These are building-size things, by the way, pretty gigantic setups. And what information is available in the map, which you'll see in a bit, is geographic location. And these switching offices are connected by about 12,000 links to each other. And it's almost fully connected. It's a directed graph. And it's directed because the flow outward is not equal to the flow inward between two switching offices. And the graph, this case study, got data every 5 minutes, and as the boldface, or at least all caps thing at the bottom says, there was an earthquake in San Francisco in 1989, and what this case study does is showed the long distance network's response to that. And the response is, not surprisingly, a certain type of overload. And so let's just show what they drew first. So their primary questions is, if you're analyzing the network in order to make it work better, where are the overloads? Which links are carrying the most traffic? Was there network damage anywhere? Presumably there might be some in San Francisco. Is there underutilized capacity so that more people, when making their calls, can have their calls routed? The caller doesn't know this, but the operating people at AT&T know this. They route some call volume through different things that are not occupied so much. Are calls getting into the affected area, or there are bottlenecks, and is overload increasing or decreasing? So all of these things are the kinds of things that a network operator would be concerned with. So let's talk for a sec about how to draw this stuff. There's a bunch of ways to indicate network edges. And so one strategy is to put a label on it. So 12,000 labels would be the outcome of that. One is to show line thickness or color. And for directed graphs, you can have two weights, one for each direction, so 116 and 29 you see there. But what they decided to do was they have a single link in which line thickness is drawn for flow to the right, it's thicker, flow to the left, it's thinner, indicating that the flow to the right is 116 and the flow to the left is 29. Now, from line thickness, you won't be able to perceive those numbers, 116 and 29. You just know that it's greater in one direction than the other, and by a rough margin of, say, 2 or 3 or 4. So, at the time of the earthquake, or at least some number of minutes afterwards, here's the drawing of the way the network looks. And as you can see, it's mega overdraw. It's the moral equivalent of the hairball, and is a little bit hard to understand visually because everybody's trying to call the same place, and so the kind of regular calling pattern is swamped by this, everybody focusing on a single location. So what they decided to do is address this problem of too many lines. The lines are causing occlusion. Long lines become more important visually just simply because they're longer, so they occupy more space and they end up overdrawing other things. And you can't see what's happening in the middle of the USA, so that's not a success. So one of the things they did to address this is to use the half and half technique that I showed on the previous slide, where the two line, the edge is drawn with two line segments, one thick, one thin, indicating the relative traffic. And they also decided to draw the most important last, and presumably what they meant was most important equals where there are blockages, and using thickness and color for traffic. And red is where you have the traffic that is at or above overload. And so here we can see sort of a straightforward version of this thing. Here we have those edges drawn, as I just said. There's, on the East Bay area, that's roughly where Sacramento is. A lot of calls going from Sacramento to South Bay to San Francisco, etc. So very heavy volume there, lighter volume here, but you're not seeing the other end of this when you're zoomed in like this. So it's a little bit hard to understand visually what's going on. So what they decided to do, particularly in order to de-emphasize those long lines from all over the country, is they shortened them all to de-emphasize transcontinental links. And so here's what that looks like. So it's a little bit better. You can see that there's, volume seems to be pretty evenly distributed throughout the continental USA, all, pointing at the same set of regions in California where the earthquake took place. So, what I've done with that case study is give you an indication of, to start with, node link diagrams, you kind of draw it in the standard manner where you complete the links. But there are some situations where it might be that you could switch your focus to draw things a little bit more economically in rare situations where, you already know the primary picture and now you want to be able to drill down into some detail. So that's the end of lecture 10.1 and kind of a revisiting of node link diagrams. Next, what we'll do is talk about interactive and force-directed graph drawing. So stay tuned.